I'm continuing the example that we have left from our previous lecture. So to find all of these values, I will just show how the process will go on. So process man, let's say. So at the beginning, if you remember, we have said that this piston falls under the effect of the equilibrium, and it falls with the constant pressure, because here you have that P of the gas, and on the other side you have that P ATM and also that weight. And since these two are constant and the P gas is constant, so let me write the processes one by one. So from 1 to 2, okay, 2 ends at, so that this one is at here. This one is 2 and this one is 1. From 1 to 2, we have constant pressure process, P process. And when it comes to from 2 to 3, and the 3 is on this stopper here, okay, and on that case you will have a different process, and let me draw that one for you too. Okay, and here you have that P0, again the weight, and these two values are constant. Okay, this one is constant, and it is equal to the gas pressure. At the beginning of the gas pressure is 1000 kilopascal. Okay, this one will be that 1000 kilopascal. It is constant, and then it touches the spring, and then you will have again the gas pressure here, and then you will have also the spring force, which is Kx by area, and this one divided by area will be the pressure. And as you can notice here is that as this one increases, this one should drop, because in equilibrium, for equilibrium conditions, as this one increases and this one should drop. And I can write this Kx by area. So I can write this one as that Kx multiplied with area and divided by area. You will have that K volume by area, and the K and the areas are constant, and it is CV. You can see that this force changes linearly with volume, and this one is drops at the same time. Okay, as this one increases, this one drops. Therefore, what you will have that from 2 to 3, you will have this pressure drop linearly. You have this spring force here that helps the gas pressure, and therefore that pressure drops linearly. And it goes from 2 to 3. Okay, and when you reach the point 3, when you are on the stopper, let me do that again. Now you are on the stopper. It rests on stopper, and on that case, again you will have just this P0, and you will have just this weight, okay? And you will have that P gas, and also supports from these stoppers as well as this spring here. And in that case, here you will have this cooling process that goes on, and therefore the gas pressure will drop from 3 to 3 prime, and the 3 prime is also at this condition here. They are at the same location, and now pressure drops, okay, but this pressure drop due to cooling. Okay, here you have the cooling process, the pressure drops, but it drops at constant volume. Here you have the constant volume, no work is done, and the pressure drops at a constant volume. So here you have that 1 to 2 constant pressure process, and then 2 to 3 pressure drops linearly with volume. I should add it, linearly with volume change. As volume changes, pressure drops linearly from 2 to 3, and from that 3 to 3 prime, you have this cooling process, and the pressure drops, and it is at constant volume. And this is the general process that we are going to have. Okay, now let's start. The system temperature of liquid vapor when the piston touches the spring. And in all of these cases, you should remember that we will be using only the specific volume. This one will be very important for this question. And each step we will need this specific volume. Now let's start. So when our piston travels from that distance to this one, to that 2 location, and you will have that volume that is enclosed by this piston with this amount, a volume at 2. So therefore, I should first find the initial volume, and then I subtract the volume here, and then I will find what is the volume here. And then from that volume, I will find the specific volume. So let's find the initial volume. Initial volume will be that new initial and multiplied with the mass of the fluid here. And it says that 2 kilograms of steam is there, and it starts with 1 megapascal and 300 degrees Celsius. The initial volume, the specific volume, I can find it at 1 megapascal, 300 degrees Celsius, and the mass is that 2 kilograms. And with these values, let me go to the chart table. And at 1 megapascal, this is the saturation pressure table. And 1 megapascal, you can see temperatures in this amount. And in our problem, temperature is more. It means that it is superheated. I go to superheated table for 1 megapascal for that 300 degrees Celsius. This is the specific volume that I am going to have. Here you will have that 0.25 and the 799 multiplied with 2 kilograms, and you will get this initial volume will be that 0.5159 meters cubed. This is the initial volume. And I'm trying to find what is my purpose. I'm trying to find the specific volume at 2. Because that specific volume at 2, and I know that pressure is constant, and from this relationship I can find the temperature, because the Gibbs phase rule says that. So you need 2 independent but intensive properties to find the third one. To find any third property, you need 2 independent and intensive properties. Okay, so let's now find it. To find the specific volume at 2, what will I do is that I will subtract the initial volume from the change of volume, and that one will be that volume at 2. That change of volume is that this distance here, which is 0.5 meter, and multiplied with the cross-sectional area of the piston. It will be 0.5 multiplied with 0.1 meter squared of the cross-sectional area of the piston, and therefore volume at 2 will be equal to 0.4159 meters cubed. That is the volume at this part here. So this is the volume that you are considering. Okay, so from this volume I can find the nu. Since the mass is constant, it is closed system, it will be that 0.4159 divided by the mass, which is the 2, and here you will have that 0.2079, that is kilometer cubes per kilogram. It's the opposite of the density. So you will have that meter cubes per kilogram. And I know the specific volume, and I know that pressure is constant. And let me write the pressure value here. It is 1000 kilopascal. And with that 1000 kilopascal pressure, go back to again saturated region table, and you have the 1000 kilopascal. Nu is that amount, and nu G is that amount. In our case, nu value is 0.20. So it is 0.20. It is more than the nu value here. It means that it is superheated again. So I go to superheated chart, and I need the nu value of 0.2079. I need that new value. You can see that this is 0.2602, that is 200 degrees Celsius. For 250 degrees Celsius, you have this amount of the specific volume. It is here in between, so I will need this linear interpolation. So linear interpolation says that you need to find the temperature, and you have this specific volume. You have 0.2602, and for that one the temperature is 200 degrees Celsius. For the next specific volume value, which is 0.23275, you have the temperature value of 250 degrees Celsius. And we assume that this one is linear, and here you have that 0.2079. For that one, I should find the temperature value here, which is Tx. Okay, by the using of the linear interpolation, you will have that 0.23275 minus 0.20602 divided by the temperature change, and will be equal to that 0.2079 minus 0.2602 and divide by x minus 200. From here you can find the temperature at that state by linear interpolation, and it will be that 203.6 degrees Celsius. Okay. So therefore, at this state, it is 203.6 degrees Celsius. So I have found the temperature for the first state. That's finished. Okay, so they calculate the temperature, quality, and the pressure when the piston stops on the stopper. So this one will be the second part of the question. Now let's find it. Go back to here. This is for the case B. And this is our device here. We have the stoppers in both sides, and the piston is on that stopper. And you will have that P of the gas, you will have that Kx by area, and on the other side you have that total 1 megapascal. This is the total pressure. And I should find this K delta X. I should find this K delta X by area force that's applied to this one, and from that one I can find what is the peak gas. So K delta X by area, and let's find it. K value is given in the question as 200 kilonewtons per meter, 200 times 10 to the power of 3 multiplied with delta X. That one is 0.8 minus 0.5. This is the delta X that I'm considering here. It is 0.3. It's 0.3. And that one divided by the area of the piston here, it is 0.2 meters squared. So it is 0.2 meters squared. That is the area of the piston. And from that one I can find the force by the piston here, and that force will be equal to that 300 kilopascal. But therefore, when you are on the stopper, the gas pressure, when it touches the stopper, it will be that 700 kilopascal. I know the gas pressure here. Okay. Now I can find the specific volume at that state, and then I can find the temperature. That specific volume, again, it will be that volume initial minus delta V. And the initial volume is, I have found it, sorry, this one is not 0.1. I made a small error here. This one is 0.2. This is the area of the piston. It is 0.2. And you will have that total initial volume is 0.5159 minus the change in volume is 0.8, the total height multiplied with the area of the piston. 0.8 multiplied with cross-section area of the piston, you'll have that 0.2, and then the change in volume will be equal to, so it will be that 0.3559 meters cube. That is the change in volume. This one is the remaining volume. And then I can find that nu will be that this volume 0.3559 divided by the mass of the gas, which is 2 kilograms, and it will be that 0.1779 meter cubes by kilogram. So I know the pressure, I know the specific volume. From these properties, by Gibbs phase rule, I can find the temperature. First, we'll go to the specific volume for the saturated region. This is 700 kilopascal, and the specific volume starts at this value and ends at this value. But for my case, specific volume is that 0.1779. It means that this part is saturated region. It is less than μg, since nu is less than μg. This one is saturated region, and for this saturated region you have one fixed temperature, which is 164.95 degrees Celsius. You have 164.95 degrees Celsius. This is the temperature at this state. It also says that find the quality, and I can do that very easily. So to find the quality, you will have that nu will be equal to nu f plus x times nu fg. And that one will be that nu f plus x times nu g minus nu f. And for this one, nu value is 0.1779. And nu f value is given in the chart at 0.001108. 0.001108. This one is the nu f value, and the nu g minus nu f value. Therefore, I should take the nu g value, which is 0.27 and 8. This is the new value. And from here, you will find that x value will be equal to 65.08%. This is the B part of the question. Now comes the C part of the question, which says that calculate the work done by the gas spring arrangement. Okay, now let's do that part and find the work done by the gas spring arrangement. First, I will find the work from 1 to 2, which is constant volume process. And then you will have 2 to 3, we have that linear drop in pressure with volume. Okay, let's first start with the 1 to 2, which is the easiest one. The work of the boundary will be that PDV, and it will be that from initial volume and the volume till spring. I will integrate it, and the pressure is constant. It will be that P, just constant P. You will have that volume till spring and minus volume initial. And this one, the gas pressure is 1 megapascal or 1 times 10 to the 6 pascals, and the volume till spring, the total volume minus 0.5 multiplied with the cross-sectional area. And I have found that quantity here. That quantity was equal to 0.4159 meters cube. It goes from 0.4159 meters cube minus the initial volume, and the initial volume is 0.5159. 0.5159. That is the initial volume. And from here, you will find that work done by the spring arrangement is that it will be 100 kilojoules, but negative. Okay, now let's look at the work done by when the piston touched the spring here. Okay, let's do that. And here you will have the stoppers, and this height is 0.3 and this height is 0.5. And the spring arrangement starts here, and this is the piston, and we have this spring here. Now to find the work, I will write the energy balance for the piston here. And before writing the energy balance, you should remember that you have correct this one and this one. This one is area squared, because if you multiply with areas, you will have this area squared. Okay, then let's calculate it, and then you will have that from this equilibrium, you will have P gas is equal to 1000 minus Kx by area. This x is variable, and this is the tricky part of the question. And the why it is tricky, because that you should have, let me give you one option. So when x is 0, P gas should be 1000 kilopascal. Okay. X0 means that undeformed spring. When the spring is not deformed, you will have the same pressure of the gas, which is constant. Therefore, I should take the x coordinate such that when it has the 0 value, the gas pressure is constant, which is 1000 kilopascal. And the x values, of course, will be selected undeformed position of the spring here. And this will be the x. This is the x coordinate. And when I select x coordinate in this manner, the pressure gas, you can see it is opposite to that one. This one is opposite to x. And therefore, you should put the negative sign here. Okay, so now let's integrate it. You will have that P gas, which is 1000 V minus Kx, and this one multiplied with area and divided by area. You will have that Kx and the volume here. So you will have that volume divided by area squared and dV. And you will go from that. At the beginning of the process, you have the volume, which is 0, because when x is 0, you will have 0 volume here, and 0 volume. And when the spring is now compressed to this part here, when the spring and the gas, you will have that volume, which is 0.3 multiplied with 0.2. This is the initial volume, which is 0, and this is the final volume, which is 0.3 times 0.2. Okay, and I have said that this one should be negative, because this, so by the x coordinate, we also mean the volume coordinate. Volume is x into area, and area is constant, and x is downwards, and these two are opposite to each other, and therefore you should put this negative sign here. And if you integrate that one, you will have this 1000 V squared and it is not 1000 V, actually it is 1000 itself. So it will be 1000 itself. Then you will have this 1000 V and subtracted from kV squared by area squared multiplied by 2, and you go from that 0 volume to 0.06, and you will get negative 51 kilojoules. This is the work done by the spring gas arrangement, and this is the work done before reaching the spring. Okay, so let me see. So we have done the C part, and the last, you see that there are three processes. From 1 to 2, you have this negative 100 kilojoules. From 2 to 3, you have that negative 51 kilojoules. But from 3 to 3 prime, this part, you don't have any work because volume doesn't change. From 3 to 3 prime, dV is 0, and therefore the boundary work is 0. This is the C part of the question, and we have finished. Now comes the D part of the question. Calculate the amount of the heat interaction. Okay, this is the first law of thermodynamics. The first law of thermodynamics says that delta U will be equal to that in minus out. For this problem, we have the in quantity, which is work in, and out quantity will be, of course, Q out, and delta U will be that U final minus U initial. Okay? And initially U, we can find it from the given values, which is that 1 megapascal, 300 degrees Celsius. This is the initial U at 1 megapascal and 300 degrees Celsius. And the final U, we can find it. The question says that the final pressure is 500 kilopascal. Okay? It will be at 500 kilopascal, and final specific volume. Final specific volume, if you remember, it was 0.1779. That's 0.17 and 79. Okay, these are the final values for the internal energy. Okay, so we can find the properties for this one. Let's first look at the easiest one, which is 1 megapascal and 300 degrees Celsius. 1 megapascal, 300 degrees Celsius, internal energy is 2793.7. It is 2793.7 kilojoules per kilogram. And you have also the mass here, which is 2 times. This is M. And then for the second part, let's look at the, again, saturated table here. For 500 kilopascal, for that amount of the specific volume, you can see it has a quality. So let's do that. That quality, that nu will be equal to nu F plus X into nu G minus and nu F. And nu value is 0.17 and 79. Nu F value is, for 500 kilopascal, it is 0.001093, 0.001093, and the nu G value is, let me go back to here, nu G value, and it is not, yes, 0.37483, it is given, 0.37483. You must subtract that one, and from here you'll get that final quality is equal to that 47.31%. From this quality, I can find the internal energy. It will be that UF plus X into UFG. And the UF value for that pressure is that 639.54 is 639.54 plus 0.4731 multiplied with UFG value, and the UFG value is also given as 1921.2. This 192921.2. And from here you can calculate the internal energy at the final state. And just 1 minute, I will write the internal energy, and that one is that 39092. Actually, this one is divided by 2. It is 1549 because I've calculated it as the total internal energy, but it should be 15 and 49. So 1549 kilojoules per kilogram. This is the U final, and I know that work in it is. I will take it as positive quantity. You don't need the negative sign here. This negative sign, it only means that it is compression, and this one means only compression. Okay, but if I specify the direction of it, you can see I didn't specify any direction here. It is negative. No direction, it is negative. But if I specify the direction, I specified it, and it will be 151. And do that calculation, and you will see that Q out from the system will be equal to 2539 kilojoules. Okay, and also, of course, not forget, multiply with the internal energy change with the mass of 2 kilograms. And this is the final value of the Q out. Now we have finished the D part of the question. We have finished C part and the B part, of course. Now comes the process on T-nu diagram. Now let's show you the process on T-nu diagram. So we have the temperature, we have the specific volume, and this chart here, I will have 3 pressure values. One pressure value is 500 kilopascal. So the first one is the 1 to 2, it is 1000 kilopascal. And then pressure drops to 700 kilopascals, and then it drops to 500 kilopascal. You will remember it. Let me go back to here. The pressure is 1000 kilopascal, and then it drops to 700 kilopascals, and then it drops to 500 kilopascal. It is given in the question that it is the final pressure. Okay. Now I will draw the pressure values here. This is for that 1 megapascal, and then you will have this, that 700 kilopascals, then you will have this 500 kilopascal. For the first process 1 to 2, we have the constant pressure, but the volume decreases. Constant pressure, but the volume decreases, and therefore I will go, and I have started from that 300 degrees Celsius, and let's say that this point is at 300 degrees Celsius. This is the point that I have started the process. Okay, and actually this one should be a bit lower. I'll draw it one more time. Because in that way you will not have this. Now it seems all right. And here the temperature is 300 degrees Celsius. I just changed the graph because, okay, the process starts here. And this one is, of course, that 1000 kilopascal. And then when the process reaches the spring value here, and also I should write the specific volume. Specific volume is 0.5159. Is 0.5159. Then it drops to 0.4159, but you should remember that this one was superheated. So the second one, 0.4159, it is at this volume. Sorry, this one is not the specific volume. Specific volume is the first one, 0.25799. Correct, it's 0.25799. This is the specific volume. That one is the volume, 0.25799. Then it drops to 0.17. That 0.20, 0.2079. But this one was this specific volume, and with that pressure it was superheated. Therefore, I'm in superheated region. So here 0.20 and 79 meter cubes per kilogram. This one is that superheated region. This is the first process. This is 1, and this one is 2. Okay. And you can check the second process. I can show you that it is superheated, 1 megapascal, and we have that 0.279, and 0.279 you can see it is 203 degrees Celsius, and it was 203 degrees Celsius, and it was this superheat region. Remember it, superheat region. Okay, second process is the linear part, and that part is due to spring, and for that one you will go linearly and end up at, so final value here. So remember the final value, you have the quality of 65%. Okay, when you touch it, you will have 700 kilopascal. I have calculated the specific volume, and I have found that it is saturated region with X is 65.08%, and the new value was 0.1779. Now let me, so 700 kilopascal, you will have this part, 0.17 and 79 meter cubes per kilo. And that process will be linear, and you will go from that way. You can see the linearity, and this is the point 3. Sorry, it's 3 itself. And then comes the last part, and the last part is that you have the pressure drops due to cooling, but it drops at constant volume, and the quality drops. It drops at constant volume from 65.08% to 47% quality. There is that. Yes, here, 47% quality, but it drops at constant volume. That one, you will have this one. And this one will be that 3 prime. This is the process from 1 to 2, and the 2 to 3, and 1 to 2 it is isobaric, and this part is the linear, and this one is isochoric. And I should say that the work for this part you can also find, so if you remember that PDV work, you can find by the area here. This one is the pressure, and this one is the specific volume. And for the pressure and the specific volume values, and we know that this one starts from the 0.27, let me write it here, 0.279, and the pressure is that pressure value was 1000 kilopascal. Was 1000 kilopascal here. This one was the initial part, and then it drops to 700 kilopascal and to 0.1779. So 0.1779 to 700 kilopascal. This is the work, and it drops. This is for the spring part, and by PD new part, PD new, and multiplied with mass, you can find this one by the area of this trapezoidal here. This one will be area of that trapezoid. Okay. This will be the area of the trapezoidal, and it is a compression work. I'm going to solve second problem on boundary work. So this problem statement is, we have 100 liters of tank. So this part is the tank with 100 liters, and it contains a saturated vapor refrigerant, and the X is 1 here, and the refrigerant is R134A, and then it is at 30 degrees Celsius. It is used to transfer it. This tank is used to transfer refrigerant from this pipe here to another device. And this device is that piston cylinder device, and this one is piston. And a minimum of 320 kilopascal is required to raise the piston. So if you write the force balance on the piston, and it has some environment pressure, it has some weight, and if you are trying to raise the piston peak gas, and this one should be that 320 kilopascal. And if you write the equilibrium force balance, you will have that P gas will be equal to weight by area and plus P atmospheric. And you can now see that all of them are constants, and therefore this process, if piston rises, so it will be at constant process or isobaric process, constant pressure process. And then the pressure is 320 kilopascal in the tank. Here we don't know the pressure value. It says that when it is 320 kilopascal in the tank, the process ends. to determine the amount of heat transfer during the process if the temperature remains constant at 30 degrees Celsius. Now let's firstly find the values for this one, and before solving the values I should select my system. So let us select our system. Okay, if you select your system as the tank here, this one, so if tank, let me give you some system options. System 1 or the control volume 1. So this one is the tank, or the system 2, you can select this one as the piston cylinder device, and you have that third option for the system, and that one is that tank plus piston device. Okay, for the first option, if you select the first option as the tank, and this one will be an open system. For this open system, you need to know the mass flow rate here, m dot. And this one, you have to know the m dot value here. And this one is unknown. This one creates problem for the solution of this one. Okay. And even if you select the tank alone, then you have to select the piston device too, because you have to find the heat transfer, because heat transfer happens into the tank as well as heat transfer happens to that system. Both of them has the heat transfer. Therefore, you have to select the tank and solve the problem, and then piston device and solve the problem. Similarly, for the piston device, we don't know the mass flow rate. Okay. But in reality, if it is a steady flow device, the mass flow rates will be the same, but we don't know whether it is steady or not. And this is also another problem here. Therefore, the better option is that if I select the tank and the piston device together, so this one and that one together, so this system will be closed system. So I'm including the tank here. Let me show my control volume for the last option. This is not actually the control volume, but this is the system. Okay, my control system will be something like this one. Okay, it includes the piston cylinder device here, and the pipeline here, and the tank itself. So when the piston moves up, the system moves up. Okay, the system boundaries moves up. So that system boundary, it changes at the when the piston moves up. Because that, we should always have that of the closed system. Otherwise, if you select this system that is one here, it will not be a closed system. And when we say that system, it means that it is closed. When we say control volume, it means that it is open system. Okay, now with this in our mind, and let's find the properties for the state 1 and solve the problem. Okay, to solve the problem, I have to write the first law for the system here. Let me write the first law. The first law is that change of internal energy of the system will be equal to that total in minus total out. And for the system given here, we have that out quantity, which is the work boundary. Okay, we have the inlet quantity, which is heat transfer. So it can be that out or in. I don't know it, but let's assume that it is in. This one is assumed. Okay, and work boundary out. And also the change of internal energy of the system, and it will be that total mass and multiplied with U final, or U2 minus U1. And let's see which one of these we can find. Firstly, U1 at the initial value of the piston cylinder device, and at the initial case of the system, you have that internal energy which is inside the tank, as well as this piston cylinder device here. So this U1 will be tank U1 and plus that piston cylinder device. And when the process starts, you don't have any energy, any mass here, and you don't have any mass inside this piston cylinder device, and therefore this term goes away, 0. And you have only the internal energy inside the tank. And for that tank, we have the X is given as 1, and the temperature is given as 30 degrees Celsius. Okay, so this one is that saturated vapor. I will go to the table for the refrigerant and find the quality with the quality and the temperature. So for that saturated refrigerant table, which is A11, we have that 30 degrees Celsius, and for that one, internal energy value is UEG, which is 246.14. This one is 246.14 kilojoules per kilogram. And the U2 value, this one also we can find it. Okay, let's find the U2 value. And if you remember, we have said that the process inside the piston cylinder device goes on constant pressure because it is in equilibrium, it is isobaric pressure, and here the pressure is constant. Okay, but here you have the drop of pressure. The pressure drops at the beginning. Let's see what was the value of pressure. It was 770.64 kilopascals. So P initial in the tank, it is 770.64 kilopascal. And this one is not constant, but the pressure inside piston cylinder device, it is 300 kilopascal, 320, and it is constant. And this one drops, and it drops to a value of 320 kilopascal, and the process stops because it is in equilibrium in both sides. Okay, now, so you have that to find the internal energy too, and you have to remember always the Gibbs phase rule. And this phase rule says that you have to know two properties, okay, and two independent intensive properties to find the third one. Here at the final state, I know that pressure, which is for my system, it is 320 kilopascal, and the one more clue in the question it is given us, the process happens at constant temperature. So now I will write the second property for this one, which is the temperature here. Temperature is 30 degrees Celsius. And for these two values, I need to find the internal energy. Let's go back to the chart here, and you can see that for 320 degrees Celsius, for the pressure table, you have this as a saturation temperature. So it means that this one is not a saturated region, but this one is at superheated region. And now let's go to find the value for this one at a superheated region, and the first one is in specific volume, then internal energy, then enthalpy, and then entropy. For this pressure, 320 kilopascals, at this temperature, you have the internal energy as 253.5. So you have that U2 will be 253.5 kilojoules per kilogram. You have found the U2, we have found the U1, and now comes the mass. How can we find the total mass? So I will take the property at the beginning of the process to find the total mass. So when the process starts, we have the mass only inside the tank. Okay, that is equal to the total mass. And that mass will be equal to the total volume divided by the specific volume, and this one will be at the beginning process. So here you have that X is 1, and then the temperature is 30 degrees Celsius. And the volume in the question is given as, that is 100 liters. This is the volume, and therefore I will have that 100 multiplied with 10 to the power of 3 and divide by the specific volume at this value. So at 30 degrees Celsius, we have the specific volume as nu G, which is 0.026622. 0.02662, and from here you will find the mass of the refrigerant, and that mass will be equal to 3.76 kilograms. That is the mass of the refrigerant as a total mass. So I have found this one, I have found that one, and this one. Now comes the boundary work here, and for the boundary work, and we have said that the pressure is constant because we have the constant weight and the atmospheric pressure, so that boundary work will be equal to and PdV from V1 and to V2. And P is constant, therefore you will have that P delta V or P V2 minus V1. At the beginning, we don't have any mass inside this piston cylinder device, therefore V1 is 0. Now comes the V2 value, and to find the V2 value here, I will use the specific volume for the second state as well as for the second state of this one. So let's do that. And firstly, so let me write it, V2 will be equal to and M2 into nu2. Okay. M2 is at the end of the process. at the end of process. And I can find this nu2 value because I know that the temperature is constant and the pressure is 320 kilopascals. So it will be 320 kilopascals at 30 degrees Celsius. And at that value, the nu2 value will be equal to, if you go to superheated table, the first one is a new value, which is 0.07231. 0.072 and the 31 meter cubes by kilogram. This is the nu2 value. Okay, so I have found the nu2 value, and now comes the mass at the second state. So to find the mass at the second state, what can I do is that I can subtract the total mass, and from the mass at the second state in tank, and that will be that mass for the second state in piston cylinder device. For this one, it is okay, and for that one in the tank, I will know that the volume divided by the nu2, but this one is in the tank. And this nu2 value in the tank, it will be at, again, 320 kilopascal, because the pressure at that value process ends, and the temperature will be 30 degrees Celsius. So you will have that. This one will be 110 to the power of negative 3, and divide by the same value here, which is 0.07231. And from here, you will find the mass that is inside the tank. So it will be 1.3938. So if I subtract that one, M total minus M2 tank, and you will have that M2 at the, so this one, let me write the value of this one, is 3.76, and you will have that mass as 2.37 kilograms, because this one is not 76, but this one is at 75 and 6, more accurate value. Here also 75 and 6. So I have found the mass second state at piston cylinder device. So if you multiply that one, so with this quantity here, let's find it. Volume at 2 will be equal to mass at 2 multiplied with the nu2 value. Mass 2 is at 2.37 multiplied with 0.07231. And here you will get, and it is also 3 here, and you have that 3 value here. And you will have that 0.71716 meters cubed, or 171.6 liters. That is the final volume. And the pressure is 320 kilopascals times 10 to the power of 3 pascal, or multiplied with this value here is 0.17, and the 16 value, you will have this boundary work. And that boundary work will be that 54.92 kilojoules. Okay. Since I know the boundary work, to go back to the equation here, it's 54.92. Okay. I know the mass here, the total mass, I have found it was equal to 3.756 kilograms. From here, I can find that Q in value into the system. And that Q in value into the system will be equal to that 82.57 kilojoules. So it means that we have assumed this one as correct. This one is correct. And also it is into the system. We have heat transfer into the system. And this is the end of the problem. So we have finished the problem here, and I stop the recording.